Hey guys, in this video, I want to talk about the difference between strong acids, strong bases, and weak acids and weak bases. And I also can go into how to take the pH of a strong acid and base because it's pretty simple. So, relative strengths of acids and bases. Now, when we say the word strong versus weak, we are only talking about dissociation. So this kind of goes back to how we were talking about solubility rules at the very beginning of the year this year. When we say something is soluble, then that means it breaks apart completely. It ionizes, dissociates 100%. Well, when we have strong acids, that's the case. Strong acids dissociate 100%. So if I have acid HA, this is just a generic form of what an acid is. When I put it in water, all of the H plus and all of the A minus is going to be separated completely. And that is if we have strong acids. Now, there are 6 strong acids that you must memorize, and we have talked about this before, so this should be a review. HCl, which is hydrochloric acid, HBr, hydrobromic acid, HI, which is hydroiodic acid. Those are 3 of the 6. There's 3 more: nitric acid, HNO3, sulfuric acid, which is H2SO4, and perchloric acid, which is HClO4. These are the 6 strong acids that you must memorize, okay? What that means, strong means dissociation only. It doesn't mean how harmful that these acids are, because they're all pretty bad, okay? It means how much dissociates. Strong acids dissociate 100%. We also have strong bases. Strong bases also dissociate 100%. Now, they're not written on here, but they are, if I take lithium down on the periodic table and I combine that with hydroxide, OH, or also we're skipping, let's see, I have to check my periodic table. Let me get one real quick. Now, if you look on your periodic table, you have first column lithium down, all right? Your second column, what you have there is you have Be, and you have Mg, beryllium and magnesium, and then right underneath that you have calcium. Be and Mg is not part of the strong bases. It's calcium down in the second column. Li down, calcium down. If those are paired with OH, then those are your strong bases. Sorry. My chihuahua is a little on the bad mood side. So those are my strong bases. Now, again, just like strong acids, what that means is it dissociates 100%. It turns into ions 100%. Okay? Now, we've talked about K values before. We've talked about K, which means equilibrium constant. We are going to be dealing with equilibrium constant for acids and equilibrium constant for bases. All right, when we're dealing with equilibrium constant for acids, we call that a Ka value. Pretty straightforward because A stands for acid. If we're talking about equilibrium constant for bases, we're going to use a Kb value. B, of course, stands for the base. Well, strong acids and strong bases have very large K values, very, very large K values. Now let's talk about how is that different from weak acids and weak bases. If we look here, weak acids and weak bases only dissociate a very small amount. All right, its dissociation is somewhere between 1 and 3% actually. Okay, so if I were to zoom in on this picture here, all right, this is what I would actually see. My HA, let's say it's a looks like this. Okay, so this is my acid. We're calling this a weak acid here. If I have my weak acid and I put that in water, what's going to happen is I might have a little bit dissociate. So there's my H, and this would actually be my A, and this is my H. They're dissociating a slight amount, but the rest of the stuff will actually stick together. It'll stay together. And we can go through and review this, and I can actually show you a good visual representation in class if we need to. So weak acids and weak bases, this behaves for weak bases too, only dissociate a small amount. Instead of 100%, like for strong, for weak, it's only around 1 to 3. Now, when we look at Ka and Kb values for weak acids, then those Ka and Kb values are very small comparatively. All right, so that's what we need to know. When we have a stronger acid, all right, so as the strength of my acid increases, let's get my writing utensil again. As the strength of my acid increases, what that means is that the strength of my conjugate base decreases. So the stronger acid, the weaker the conjugate base. Same thing goes for strong bases. The stronger my base is, the weaker the strength of my conjugate acid is. Now we can relate the strength of an acid and a strength of a base. We can kind of compare different acids and different bases, and it's all based upon the K value. As your Ka value increases, the strength of the acid increases. If your Kb value increases, the strength of the base increases. Now, all that this relates to is how much is dissociating. Different acids dissociate differently, unless you have your strong acids. All of your strong acids dissociate 100%. But if you have all of your weak acids, any acid that's not these 6 you have to memorize, they have different strengths comparatively. So what I can do is look at their Ka values, compare the Ka values. Well, the stronger my Ka, or the higher my Ka, I should say, the stronger the acid. But when that acid dissociates its proton, when it donates its proton, that conjugate base is going to be very weak. All right, so we need to realize this relationship here. Same thing for bases, all right? As my Kb value increases, the strength of the base increases, but once that base accepts that proton, that conjugate acid is going to be very weak. So they like to ask this in multiple choice, and hopefully you'll be able to get those answers if you can understand these relationships. One other thing I want to relate to as far as strength is what we call oxyacids. An oxyacid is an acid that has a bunch of oxygens in it. So you see this table. This is actually on page 5 of your NIMSY packet. If we have oxyacids, they have different strengths comparatively. And I can actually figure out which of these are stronger according to how many oxygens they have. Here's the rule. The more oxygens you have, so the more oxygens you have, Bo, hush buddy, equals the stronger acid. So the more oxygens you have is equal to the stronger acid. So if we compare HClO to HClO2 to HClO3 to HClO4, remember HClO4, that's one of our strong acids, right? That's one of our 6 we have to memorize. So HClO4 is a strong acid, but these guys are weak. It's something to do with that oxygen. Now, HClO3 is stronger than HClO2. So what's the trend here? What's actually happening? Yes, the more oxygens we have, the stronger the acid. Now, you can't just explain this in a justification. You have to explain why this is the case. So I've seen some free response questions where they say, okay, well, you have HClO4, it's a strong acid, but HClO3 is not. Justify why this is the case. And so this is what's happening. Oxygen is electronegative. It's highly electronegative, I should say. Now, what electronegative means is that it attracts electrons. So let me write this down here. Electronegative means, hush buddy, that it attracts electrons. All right. Now, oxygen is highly electronegative. So when I add more oxygens, what's happening is you're actually attracting the electrons away from this hydrogen. So you see here, the oxygen's here. I'm only pulling a little bit away from the hydrogen. This one, I have 2 oxygens, so I'm pulling double the amount away from this hydrogen. This one has 3 oxygens, so I'm tripling the pull that I have away from this hydrogen. And this one has 4, so you get the idea. I'm quadrupling the amount of pull away from this hydrogen. I'm pulling those electrons to one side of the molecule. Now, when you pull these electrons, hold on just a minute. Sorry, I have a visitor. Sorry, my dinner's ready. My chicken is waiting for me. I'll finish the video first, though. Sorry, like I said, if I have more of a pull of these electrons on one side, we call that electron density. So what's happening is the electron density is increasing away from these hydrogens that you have here. So there's my hydrogen, there's my hydrogen, there's my hydrogen, there's my hydrogen. So as you're increasing your electron density away from your hydrogen, what it's doing is it's leaving this bond, this OH bond right there, very weak. Think about like having a rope like tied to like a pole or something, and you have like 1 strong man pulling the rope versus 2 strong men, 3 strong men, 4 strong men. Well, what's happening as you add more people pulling onto that rope is getting weaker and weaker. Well, as it gets weak enough, that rope is going to snap in half. And when this rope snaps in half, guess what? This little hydrogen is going to pop off. And what is the definition of an acid? The acid's defined as a proton, an H+, being given off, right? Being donated. So, as you're adding oxygens, you're increasing the probability that this will happen. And so that's why adding more oxygens makes a stronger acid. So, I talked all about it and everything. I gave you an example. How do we justify this on a free response in order to get credit? So what I would do, here's my question again. HClO3 is not a strong acid, but HClO4 is. Justify your reasoning. What I would say first, and you put these in sentences, these are just the bullet points that you want to talk about. You would say that HClO4 has more oxygens. I'm just going to shorthand this. More oxygens than HClO3. Step 1. All right. Step 2. You talk about as more oxygens are added, so as the number of oxygens increases, number of oxygens increases, you get the idea, then that actually increases electron density. Now again, what electron density means is that the electrons are being pulled away from this bond here. It's being built up on one side. Dense is being built up on one side. Because you are increasing the number of number of oxygens, which increases the electron density, this actually makes an increase in electron density actually makes the bond weaker. So equals a weaker OH bond. And if you're making this OH bond weaker, what that means is it doesn't take as much energy to chop that off, right? It doesn't take as much energy to dissociate that. So step 4 is less energy. You always want to talk about energy because that's what chemistry is. It's the study of matter and energy. So you want to talk about energy. So less energy is required to break the bond. And if less energy is required to break that bond, it dissociates more readily. And if your hydrogen right here is dissociating more readily, that is equal to your stronger acid. So this is kind of the bullet points you want to talk about when it's asking about oxyacids. The more oxygens you have, the stronger your acid. You have to justify why that's the case. Before we leave in this video, I want to talk about strong acids. Remember we said there's 6 of them we have to memorize. And it dissociates 100%. That means all of the ions are separating, your hydrogen's dissociating or being donated 100%. All of the H pluses, actually. And so how do we figure out the pH of these strong acids? Well, hopefully you've learned by now from the calculating pH worksheet that you've worked on that you can calculate the amount of hydronium ions and you can calculate the amount of hydroxide ions. If I have more hydroxide ions, then that means that the solution is basic. If I have more hydronium ions, then that means that the solution is acidic. And I can actually put a number to that, which is called pH. You also have a POH, which is dealing with bases. So POH is dealing with bases, pH is dealing with acids only. So here are the equations that you need to know. pH is equal to negative log of your hydronium ions, which is H3O+. You should have found this to be true when you were working your worksheet there on calculating pH. You also have POH, which is equal to negative log of the OH concentration. OH minus concentration, your hydroxide. And then if I take pH and I add POH, you should always get a number, which is 14. And that's why our pH scale is 1 to 14. From the worksheet, you notice that if I take H3O plus times OH minus, it's always 1 times 10 to the negative 14. Well, if I take the log, a negative log actually, of 1 times 10 to the negative 14, guess what number I get? 14. And so that's why our pH scale is 1 to 14. If you have a number for pH that is less than 7, then we classify that as acidic. If it is greater than 7, we classify that as basic. And if it's exactly 7, we classify that as neutral. So how can I take a strong acid and figure out its pH? Well, the pH of this strong acid is found by pH equals negative log of H3O+. Well, I know HNO3, I know its concentration is 0.1, but how do I figure out the pH of H3O+? Well, this goes back to our definition of strong acid. It dissociates 100%. So what that means is whatever the concentration is of the HNO3, that is exactly equal to the concentration of the H3O+, because all of it is being dissociated 100%. So what I do to find the pH of strong acids is I just plug in the molarity of the strong acid in this equation. So I get pH equals negative log of H3O+ concentration. So I would take negative log of 0.1 molar, which equals 1. If I'm working with a strong base, how do I calculate the pH? Well, strong bases aren't giving more H3O pluses, they're actually giving more OH minuses. So what I have to do first when I have a strong base is I have to find POH first. I take, let's say if I had 0.1 molar NaOH, which is a strong base, the concentration of the NaOH is exactly equal to the concentration of OH minus. Why is that? It's because it dissociates 100%. If it wasn't a strong base, it wouldn't do this. I'd have to figure out a different way to find the pH. So my first point is to take this molarity, plug it in for the OH concentration. But the problem there is that I know a POH. I don't have the pH. So my next step is to take pH plus POH is equal to 14. So whatever number I found for this portion, I'm going to plug in right there. Subtract that number from 14, and that gives you your pH. So that's how we find the pH of strong acids and strong bases. Very simple. We just basically plug in those concentrations into the appropriate equation and solve for it. How we figure out the pH of weak acids and weak bases are a little bit different because it's not dissociating 100%. So that we are going to do on a different video. So I hope this is helpful. Sorry for the barking. Sorry for the interruption. I'm going to go eat my dinner now. Hope you have a good one.